So this week we are talking about semantic knowledge, which theoretically you could think of as literally the third module where we're talking about memory because semantic knowledge is literally just like another way of talking about semantic memory. So here are the topics that we're going to be covering. We'll start with some general ideas about concepts, categories, just like semantic knowledge in general. We'll then talk about the three different approaches to categorization that have come out of the cognitive psychology literature in collaboration with philosophy, interestingly. We'll then move on to talk about models of semantic networks. And I'm going to talk a little bit about artificial intelligence there because this is where cognition literally meets artificial intelligence. And, I think people kind of think of artificial intelligence as an emulation of human intelligence, but I actually think it's better characterized as an emulation of human cognition. And then we will finish up by talking about what babies know, which is frankly a creepy amount. I don't know about what you guys think, but babies are creepy. I'm just kidding. Babies are adorable, but they can be, it can be shocking, the things that the babies know. So we are going to start with knowledge and the idea of concepts and categories. So how you organize stuff depends on how you use it. This section is really about how information is represented and organized in semantic memory, but it's also how we use semantic information, and those two things are really intimately related. It's like where you put things in a kitchen. You put stuff in the most easily accessible places. So for most people, how you use a kitchen influences how you organize a kitchen. It's why you can go into somebody else's kitchen and actually predict where their cups are going to be or where their flatware is going to be, because how you use a kitchen dictates how you organize a kitchen. When it comes to conceptual semantic knowledge, there are some really interesting commonalities among people in the way they both organize and use information. So let's start with some sort of basic definitions, starting with a concept. So a concept is a mental representation. It refers to all of the knowledge that you have about a particular category, and it's what allows you to make inferences about new examples. So what is a cat? You have a mental conceptual idea of what a cat is. So categories are, categories are a way to organize concepts. So these are things that are grouped together because they have perceived similarities. A category is really a collection of instances that are treated as if they are the same on some level. So you have a concept of a cat, you're going to treat like tabby, Siamese, Russian blue as perceived similar instances and put them into a category together. And then finally, categorization involves using concepts to place objects into categories. So we're going to look at how do we form concepts, how do we categorize things, and how do categories get formed. So concepts provide rules for sorting objects into categories. Like a concept, when I say a house, it might include ideas about home, family, but it might also include things about the structure, like the abstract, concrete knowledge that you have, also the different instances. But the category of house might have things like duplexes, split levels, mansions, ranches, farmhouses. When I give you an example of an object like this, you're going to use your concept of a house to categorize this particular example of a house, even though it's maybe different from your typical concept. And then again, categorization is how it is that we use concepts to place objects into categories. And Bruce Goldstein, I used to use the Bruce Goldstein textbook for this class, and one of the smartest things I think he put in his textbook was this. I'm going to read this quote actually. If there were no such things as categories, we would have a very difficult time dealing with the world. Consider what it would mean if every time you saw a different object, you knew nothing about it other than what you could find out by investigating it individually. So categories are actually really useful. They're like instant knowledge. I actually went through a little exercise because I was sort of curious to see if GAI, generative AI, could emulate the experience that a person might have if they didn't have categories or concepts. And so encountering a coffee cup that is not their coffee cup, they've never seen this particular coffee cup before. So they are oblivious to what it is they're looking at. I asked for ChatGPT to sort of give me the response that somebody might have if they didn't have categories and encountered this object here. I found it on the counter this morning, a small round vessel with a handle, smooth and cool against my fingers. I turned it over, studying the shape, the thickness of the rim, the faint scent of something bitter clinging to the inside. It seems that something could be put inside. A candle? Liquid? I pour in some water, testing it. It feels strange. Too shallow, too heavy, somehow wrong. I wish I knew what it was for. Every new thing I come across asks the same exhausting question. What are you? And each time I have to begin again as if the world has never told me anything before. Very dramatic. But I did think that was like sort of an interesting exercise to think like, what would it be like if you didn't have categories? And literally every object that you encountered would be a complete question mark until you figured it out all over again. And in fact, the idea of a handle, that's also a category. You wouldn't even be able to bring up a handle, my friends. So literally, we need categories. They are fundamental to how cognition works, and they are very useful. They tell us things instantly. So categories literally help us make inferences about new cases. We recognize this as an example of part of the category cat. And from there, we instantly know a couple of things. So it's going to like milk. It's a carnivore. It's going to scratch up your furniture. And if you die and you don't arrange some sort of food delivery system as an alternative, it will eat your face. So literally, you don't have to figure this all out. You don't have to get to know this particular cat in order to be able to make some inferences about what it likes, what it's going to do, how it's going to behave, etc. So it's instant knowledge. At this point, you're capable of taking a little pause here and heading over to the Moodle page and finishing up concepts and categories, HPIP activity concepts and categories, right here. That's the thing. So how are objects placed into categories? Let's get into it. There have been essentially three approaches proposed about how people place objects into categories, and I think it's really useful to compare them head to head to start before actually jumping into them in more detail. So the first approach is the definitional approach based on some definition, and that definition is going to include the features that are necessary and sufficient in order for an object to be included in a particular category. So if a dog meets all of the listed features here, those are necessary and sufficient for an example to meet the category definition of a dog. There's also the prototype approach, which is based on averages. Rather than actually looking at an example, the prototype approach it imagines that people take all of the specific instances of a particular category and they've come up with some average of that category. This is why for this example or for this approach, I have a schematic icon of a dog here, because the prototype approach, your prototype for that category is not going to be a real example of the category. It's not going to be a category member, but it's going to be some idealized or averaged version. And yeah, so it's something more like a schematic version. And then the last approach is the exemplar approach. So the exemplar approach, we place objects into categories based on specific examples. So we keep track of a particular category using not just like one idealized average, but actually all of these specific instances. So for the exemplar approach, you would represent the category of dog with literally different examples of dogs, like a German Shepherd, there's a Boxer, Chihuahua, Labradoodle, Havanese, I think. So you've got the category based on specific, actual, real examples of category members. Okay, so let's go back and talk about each one of these in detail, starting with the definitional approach. So, according to the definitional approach, something is a member of a category because it meets the category definition. If we came up with a category definition for dogs, probably it's going to include things like four-legged, furry, barks, has a tail. There might be some other ones there, but like I think that those are ones that sort of come up a lot when you ask people about how they might define a dog. And so here we've got like another set of definitions, but here what I'm talking about is the specific features that are necessary, and these are sort of physical features. So let's consider these physical features that we've just named. So four-legged, furry, has a tail. So here's the thing. With the definitional approach, not all members of categories have the same features. So it's either going to be impossible to create a definition, or any definition you do create are going to leave out some really obvious members. The solution actually came out of the philosophy literature, and it's called family resemblance. The concept is that categories can be based on similarity of shared features that are not necessarily shared by all members. And it's actually based on the literal concept of family resemblance, because family members can look alike without all sharing the same features. And the point is that they share some features. This, by the way, I have no idea who this family is. I just Googled family resemblance, and this is what came up in the image search. And amazing example, because that is some strong familiar genes. So you don't actually have to share all the features. You can just share some of the features. This concept allows for variations in the category. The common features depend on what subgroup of the family you're considering. So some family members will have the same hair color. Some family members will have the same shape of eyes. Some will have similar body types. But we can apply this to non-family categories also, like dogs. Most are going to have four legs. Lots are furry. Many have tails. But there are different body types, colors, fur types, faces, etc. So with family resemblance, there's no pressure for every member of the category to meet the same set of criteria, only a subset of criteria. And that subset is variable. The concept of family resemblance actually inspired researchers to propose the next approach, the prototype approach, because it seemed like the categorization was based on similarity with some standard representation of family. So the typical prototype is based on the average members of a category that are commonly experienced. So it's like a summary representation that captures like the central tendencies of a category. The reason that I'm using this image here is because these are actually images that were created by researchers and that are literally the average of a group of German men on the left and German women on the right. So these are not real people. They don't exist in real life. They are the average of a number of people. So the prototype is never an actual member of the category, but an average or an idealized category member. And then the question is the test exemplar similar to that prototype? And the prototype approach uses the notions of prototype and prototypicality. Prototypicality refers to how well an individual resembles the typical member, and an object with high prototypicality means that the category member closely resembles a typical member of the category. Low prototypicality means that the category member does not closely resemble a typical member of the category. Typicality involves making judgments about how well objects represent particular categories. And one of the things that this approach suggests is that membership is graded. So graded membership refers to the fact that objects which are closer to the prototype are better members of the category than objects that are further away from the prototype. So, for example, if you name a piece of furniture, you probably would have written down something like chair or sofa. You're very unlikely to have written down something like telephone. Similarly, if you were asked to name a bird, you'd probably name something like a sparrow or a crow, maybe, if you're in Vancouver. But you're very unlikely to have named a bat. So, sparrow is a good category member for bird. Bat is a bad category member for bird. Makes sense because actually bats aren't birds. Research around the prototype approach suggested that good members have high prototypicality and high family resemblance. This image, by the way, I found it was created by an artist who took family members and merged their photographs together so you could literally see that family resemblance. I thought it was a really interesting representation of the idea. One of the most popular paradigms in cognition is, especially around semantic knowledge, is the sentence verification task. And on this task, you really just have to decide if a sentence is true or false. So I'm going to show you a couple of examples. It would be presented on a screen like this at center. You would be fixating the plus sign, and then you would be presented with a statement. A shirt is a vehicle, true or false, and you just need to indicate false here for a correct answer. A pomegranate is a fruit, true. An apple is a fruit, also true. So if you look at an object's prototypicality rating, it correlates with the reaction time in a sentence verification task. So you're going to be faster to verify that an apple is a fruit compared to a pomegranate is a fruit because an apple has higher prototypicality than a pomegranate. This is referred to as the typicality effect, the finding that people are faster and better at recognizing or processing more typical examples of a category compared to atypical examples. So good category members have higher prototypicality and faster sentence verification. And we call that the typicality effect. And they're more likely to come up on a production task. If you simply ask people to name objects from a particular category, like for example, in the next 60 seconds, name as many animals as you can, they're going to tend to name objects or examples that are more similar to the prototype. So what's the prototype for animals? Interestingly, I decided to do a Google image search for the word animal and see what came up most often. I think that the prototype for an animal is literally four-legged and furry. Even though there are lots of animals that don't fit that category, I think that our average is actually four-legged and furry. So do you remember that song? What does the fox say from a few years ago? Dogs go woof, cats go meow, birds go tweet, mice go squeak. Some of these are making it in. Birds probably would not be considered high in prototypicality for the category animal, but dogs, cats, and cows probably would. Foxes maybe would be somewhere in the middle. Elephants actually would be low, I think. They're four-legged, but they don't have fur, and they're kind of unusually enormous. Um, uh, Ducks. What is that one again? Ducks, fish, seal. Uh, okay, so fish and seals, not high in
Dog goes woof, cat goes meow, bird goes tweet, and mouse goes squeak. Cow goes moo, frog goes croak, and the elephant goes toot. Ducks say quack, and fish go blub, and the seal goes ow, ow, ow. But there's one sound that no one knows. What does the fox say?
I like to share my weird sometimes, even in recordings. I want you to think the color green, and I want you to mentally select one of these greens as the green that you think matches the color that you're thinking of. My guess is that it is, if we did A, B, C, D, my guess is that you would be selecting C right here. And that is because even colors can have prototypicality. So if you prime someone with the word green, people tend to think of the prototypical green, the most idealized average version of green. And it turns out that if you prime people with something like the word green, that prototypical green is going to experience faster, stronger priming. So here's another paradigm that researchers love, cognitive researchers love, is priming. In a priming task, you present a prime that you tell participants that they can ignore, they don't need to respond to, followed by a target. That's the thing that they need to respond to, and they're usually making some kind of judgment about it, and that judgment can vary pretty tremendously. Here, for example, we might ask people whether or not these two color samples are the same color or are different colors. And here the answer is same. And then we would compare it to trials where the targets were same, but you have that very Kelly green, Kelly, that very high prototypicality green, and compared to a sort of washed out sage green, which has lower prototypicality, and then compared to an unprimed target. So literally where the prime and the target do not match. Now, in the module on Moodle, there is an activity here that's meant to help you work out what it means by stronger priming. Think now about the pattern of reaction time you might expect that would show you what stronger priming looks like. But I also want to take a moment to tell you about what faster priming also means. So just take for granted that you understand stronger priming. Faster priming is when the interval between the prime and the target can be really short, and you're still going to see a positive impact of the prime on the target. So people are still going to be faster to respond to this version of green compared to the other one, even if you only show the prime for like 250 milliseconds. Like, you're going to see priming show up real quick. So you don't need a really long exposure to the prime to see that benefit. So that's what that means when it means faster priming. It's actually not about your reaction times. It's about this duration between the prime target interval. All right, now let's look at the exemplar approach. According to the exemplar approach, something is a member of a category because it is similar to an exemplar. And exemplars are actual members of the category that a person has encountered. And when I think of my exemplars for the category of dog, it's like big dogs like Great Danes. It's going to be tiny dogs like Chihuahuas and Pomeranians, and it's going to be literally like everything in between, the short hairs, the long hairs, but it's going to be those specific examples that I have encountered in my life, whether or not those are specific breeds or whether or not those are literally specific examples, like my family's dog that I grew up with, Shogun, or the dog that I had as an adult named Gracie, who was a mini Australian Shepherd and the laziest dog who ever lived. I love that girl. Miss her. Okay, so if you ask me to name a fruit, or if I asked you to name a fruit, you'd probably name something like apples or bananas, but not because apples resemble the average of like the category member. And like, I don't even know what the average of a category member for a fruit is. Is it going to be the average of an apple, a banana, an orange, and a pineapple? Probably not. But because they're both exemplars of the category, they actually come up quite frequently or very highly in a production task as because they serve as exemplars for the category. So, in the exemplar approach, things like blueberries and cherries and watermelon and grapefruit and kiwi can all be are all represented not by an average, but by those specific examples. So, interestingly, it turns out that the exemplar approach can also explain family resemblance, sentence verification task, the production task, and results from priming. So in a production task, if you name some fruits, you're going to name fruits that you tend to be most familiar with. You're not going to name these fruits because they all resemble some prototypical average. And similarly with sentence verification task, these are all highly familiar exemplars. They're not high in their prototypicality. The advantage of the exemplar approach is that it can more easily take into account atypical cases. For example, non-flying birds. Not flying would not be part of our average for birds. But we do not have much trouble at recognizing these examples as birds. So how do we do that? We use exemplars. Then the question becomes, which one is right? So we've thrown out the definitional approach. It's not that one, right? Like that is not flexible enough. It does not explain how people put objects into categories. But we can now choose between the prototype approach and the exemplar approach. Which one do we use? The answer is probably both. And I think that if I haven't been able to find a study that actually demonstrates this explicitly yet. It might be out there, but I haven't found it. However, um, what what I do think is, first of all, categorization is actually important enough to cognition to get redundant expression, right? So like redundancy in the system for something that is so critical to cognition makes a lot of sense. But there is, I think, if I squint and I look at the literature, I do think I see that we start by using the exemplar approach, and or we actually kind of maybe we start by using the exemplar approach. But the first time that you encounter something like a palm tree, it's hard to tell, are we dealing with the prototype approach or are we dealing with the exemplar approach? Because literally the average of one is one. So it might look like you're using the exemplar approach to start, but maybe you're actually immediately defaulting to the prototype approach. However, what it looks like is that after that first encounter, people very quickly start creating an average. So that after you've encountered a few different examples of palm trees, you start to create these idealized or schematic version or this prototype version of it. And probably your prototype of a palm is going to include like a long trunk and palm fronds, right? But with more experience, you might actually start to come to recognize novel examples of the category that actually are really atypical examples. So, for example, this is a specific type of palm tree that has a very short trunk. And so it kind of looks more like a bush, but it's considered part of the palm tree family. Some unusual category members will never be included in the average and always need to be represented as exemplars. What I think this means is that experts are more likely to rely on exemplars than novices. They have more experience, and so they can represent more specific knowledge. But in contrast, when people are animals need to identify a whole category of objects, categorization is actually probably best served by generalization. So I kind of suspect that it starts out, I actually kind of think we start out prototype immediately, start creating an average that we use for categorization until you reach a level of expertise that atypical examples start to become problematic and you start to represent them as exemplars. All right, here's the point in the lecture where you can go and complete the H5P activity, how are objects placed into categories, approaches. I also would like you to take a moment to complete the forum, hot dog, not hot dog. I've set it up so that each one of you need to individually answer the question that I have posted there before you're going to be able to see everybody else's answers. Once you answer, though, all of the other people who have answered that question, their responses will become visible. And I want you guys to think critically. I want you to put the answer down, and then I do want you to see what everybody else is thinking about this. I think that's a useful activity. Try not to use generative AI for it. Try to just like answer it, but you do you also. So, how are concepts or categories actually represented in the mind? The answer here comes from models of semantic representation. Now, let's go back to the symbol manipulation model that we talked about in the very first module for a second. Here, the symbols are meaningful and they contain most of the information relative to a particular concept, except the relationships. The relationships then end up getting defined later as the connections between these particular symbols. And so a computer program for this kind of semantic model representation would actually look something like this. You would need to tell the computer to make these symbols, 1 to 6 symbols for this sort of small scale model, and then each one of those symbols you need to define in detail with all of the specific characteristics that you have related to that symbol. So you would be able to say the Doris symbol has brown hair, blue eyes, is a female, and is a lawyer. The Herman symbol, on the other hand, would have brown hair, brown eyes, is male, and their job is a teacher. And then the definition of the relationship would come afterwards explicitly, that the relationship is that Herman is married to Doris and Doris is married to Herman. This is how you would program this kind of symbol manipulation model. And you can see it's kind of clunky, right? You literally have to go through and know all of the specific features of each one of the symbols before you even get started. Moreover, if you forgot to program in that a golden retriever is similar to a cocker spaniel and that they are both types of dogs, then you now have no way for this model to realize that a golden retriever is similar to a cocker spaniel. Even though they're both dogs, the system doesn't realize that that's because they're similar. And so if you forget to program that in, like your model does not work effectively. Or if the program encounters a new breed of dog, it would have zero idea what to do with it. It's not even an animal, let alone a dog. So the symbol manipulation models were just the first step. They really just got us thinking about how this might work and how we might program them, but they were not at all how cognition worked. They didn't actually effectively represent cognition. Moreover, they ignored how cognition is implemented in the brain. We do not have these high-level symbolic neural nodes in our brain. We have neurons. Neurons don't know anything. It's the pattern of activation across the system that keeps information. Collins and Quillian were a set of semantic knowledge researchers who wanted to use semantic network, or started this. Basically, Collins and Quillian is one of the first models of semantic networks in human cognition. And it was similar in concept to Simon and Newell's logic theorist model, which the last slide, that even quite wasn't Simon and Newell's logic theorist model, but it was kind of similar to that. But Collins and Quillian's model incorporated the fact that information in semantic memory seems to be hierarchically organized. So more general concepts are going to be stored at the top of these models and more specific concepts at the bottom. And the whole thing is structured from nodes and links. Categories or concepts are represented at the nodes, but the links between nodes represent the relationships. And related concepts are going to be connected in sort of logical ways. So you started at the top with this like general category of living thing, and you have all of the specific features that apply to all living things at the highest level in the hierarchy that you can, so that those characteristics apply to all other instances lower down in the model. So living things grow and are living. That also applies to plants and animals. Those are sort of lower level in the hierarchy, and those further break out down into specific instances. So to access information about a salmon, you would start at the salmon node. And at this node, we can learn that a salmon is red. So specific features for specific exemplars that don't apply to all of the other examples in the model are going to be stored at the node where they apply. So salmon is red. That's specific to salmons. But if you move up a link, you can learn that a salmon is a fish. And like other fishes, salmons have gills, can swim, have scales, and also is an animal. At the level of animal, we can also learn all sorts of things that also apply to salmons, like they can grow and they're living. So nodes represent a category or a concept, and links represent the relationship between those nodes. Something illustrated in the connections is the concept of cognitive economy. So cognitive economy is the fact that shared features are represented just once. Like, for example, plants have roots right at the top, right at that node of plants, because that applies to all of the other examples that fall below it. You don't need to recode that multiple times. It makes more sense to have that stored only once. So cognitive economy makes it difficult for exceptions to be represented. To get around this, Collin and Quillians assumed that unique properties or exceptions are going to be represented at the lower level nodes where they apply. So for example, at the node of an ostrich, you can see, or at the node of a penguin, you would both have a link to another node indicating can't fly. And that's part of the interpretation of cognitive economy. It's actually most economical to store exceptions at the node where they apply. All right, so something that I need to explain before we talk more about priming is the idea of spreading activation. This is essentially the idea that the activation of one node or unit in a network spreads to nearby nodes or units. And this is the entire explanation for priming. You activate a concept like dog, like you present maybe dog as the prime, and you're going to see that that activation is going to spread to nearby concepts like barks or animal or friendly. Retrieving one concept from memory is going to trigger spreading activation to other nearby locations in the network. So you prime concepts then become easier to retrieve from memory. So when a node is activated, activity spreads out along all connected links, and it's going to activate those nodes closer by more strongly compared to more distant nodes. So we can see evidence of spreading activation in a lexical decision task that uses a prime target paradigm. So a lexical decision task involves asking a participant to decide whether or not a letter string is a real word or not, and it usually comes in the form of a priming experiment. So you would present participants with a prime word and tell them that this word they can ignore this word, they don't have to make any response to it. And then you present the target, and you tell the participants they need to judge whether or not this letter string is a real word or a non-word. So here, chair is the prime, money is the target. You make the decision about whether or not money is a real word. So here, yes, it's a real word. In this example, you can see that the prime and the target are unrelated. So the prime should not improve processing of the target here because they're not related. However, if the target is related, so for example, the prime is chair and the target is couch, what you're going to expect is that participants will be will be faster to respond when the prime and the target are words that are associated with each other compared to when the prime and the target are not associated with each other. And that time difference, that reaction time difference, refers to the priming effect. So how strong priming is depends on the difference. The bigger the difference between words that are associated versus not associated, or primed versus unprimed conditions, that dictates the size of the priming effect. This model makes some predictions. So first and foremost, with the sentence verification task, people should be faster to respond to statements that include properties or concepts that are close by. For example, when you give a participant a sentence that involves confirming the categorization of a canary, people should be faster to confirm that a canary is a bird compared to a canary is an animal, because to get to that node, it needs to go further. And that's true. And when you give participants a sentence that involves confirming properties of a canary, people should be faster to confirm that a canary can sing compared to a canary has skin. And that's also true. So here you can see that the red line represents confirming the category, whereas the dotted blue line represents confirming the category properties. And in both cases, the further you have to go in the model, the longer it takes participants to respond. That prediction is confirmed. But the first criticisms had to do with the typicality effect. Remember, this is the ability to judge highly prototypical objects more rapidly than less prototypical objects. And it turns out that a canary is a bird can be verified faster than an ostrich is a bird. But according to the model, these two questions should take exactly the same amount of time to verify. Or an apple is a fruit compared to a pomegranate is a fruit. That cannot be explained through Collins and Quillian's semantic network models. There was also some evidence against cognitive economy, evidence that specific properties shared by other concepts are still being stored at the node for that particular concept. So for example, people were faster to verify that a pig was an animal compared to a pig was a mammal. According to the model, a person should have to travel up the links to reach mammal before they get to animal, but that is just not the way they behave. Other semantic networks were proposed. Like, people made some adjustments to semantic network models that were meant to account for some of these criticisms, but they all had serious problems that eventually inspired a different approach, which is the connectionist models. So remember, we talked about these connectionist models also in the very first module. According to the connectionist approach, concepts are represented as patterns of activation across nodes in a network. The nodes themselves do not have any information. They're abstract entities devoid of interpretation. The way that the literal computer program might look is something like this. You would tell the computer program to make these 30 abstract nodes. You would define what a golden retriever is. So what's the pattern of activation for a golden retriever? You could define what the activation is for a cocker spaniel. And then you could create this rule that if there's overlap, you need to make a category. And here I'm presupposing what that category name is: dogs. But you can see here that now, something that naturally emerges in the way that the information is represented is, first of all, that golden retrievers are similar to cocker spaniels, and the category emerges out of that similarity itself. So you don't need to explicitly tell the model about these similarities. It's literally already represented in these patterns of activation. So the connectionist approach with semantic network models, these symbol manipulation models, specific categories are represented in individual nodes in the network. In connectionist models, specific categories are represented via parallel distributed activation. So the connectionist approach actually took into account how neurons work. Specific categories are represented by distributed patterns of activation across the system, which is also how neurons work. So using the connectionist approach presupposes that there are going to be different input units. So different units. Input units are units that are activated by stimulation from the environment. Output units are the units that contain the final output of the network, and then hidden units are located in between the input and output units. One of the important features that you can't see here is the connection weights. So the hidden units help to dictate the connection weights between these all of these different units. And connection weights determine how signals sent from one unit either increase or decrease the activation in the next unit. Imagine that you have some input, and you can actually think about this as like a prompt in an AI system. It could be like the question that you're asking. You might be asking about a particular category. That input is now limiting what's likely to be activated based on these connection inputs through the hidden units. So activating that second gray input unit, it has strong connection weights to these two green hidden units, which themselves have the strongest activation to that second output unit. But you can see that there's going to be a pattern of activation generated even by just like activating that one input unit. You're going to see a pattern at the output level. You're going to see a pattern of activation based on the connections between the hidden units. So this is sort of a schematic representation about, that was a schematic representation representing those connection weights. But here I wanted to show you what that ultimate output might look like. It's going to look like a schematic of activation, or a pattern of activation. And the advantage here is that you can now represent a number of different instances in the category by the same units. It's just a different pattern of activation. Something else that's really a strength of the connectionist approach is that it's very robust, which means that, for example, if you lose neuron 4, those patterns of activation still are relatively maintained. So you won't be able to, like, it's not like you're going to stop recognizing Bill, Mary, and Raphael because you've lost neuron 4. The pattern is still basically there. So according to the connectionist model, there's no hierarchy of concepts. There are different nodes that kind of do different things, and the connection weights between them determine how the overall system will respond. So this is a very small contained example of a connectionist network, just to illustrate a point. If you activate some concept unit like canary, and a relationship or a relational unit can, so you literally type in a canary can, that's going to, a canary activates that concept, can activates the relational, and the combination of those two activations are then going to be passed on through different connection weights to various hidden units in the system that will ultimately only stimulate some of the possible responses. With a canary can, you're now going to be limited to, in the system, you're going to be limited to grow, move, swim, fly, and sing. But keep in mind that you can't see the connection weights, only the results from the connection weights. And even then, you're with the limitations of grow, move, swim, fly, sing, there's still going to be some that are going to be represented more strongly than any of the others. Other than swim, right? Like a canary can swim, it's very unlikely to be represented, or it's very unlikely to be the strongest connection weight and the ultimate response that gets selected. Instead, probably fly is going to be the number one that gets selected. Sing will be up there. Move will probably be positively associated, but not strongly. Grow, same thing. Swim is maybe even going to be negatively associated, so that it's suppressed in this model. So selection is based on connection weights that dictate which properties will be activated by which concepts and relations. Connectionist models are also referred to as parallel distributed processing, and I wanted you to see the relationship between these sort of like schematic representations of the abstract model of a connectionist model, and then the final output that can be represented as this sort of pattern of activation in a graph. What I want you to think about is that the final output units, that pattern of activation across those output units, is now just being translated into 8 units of output in a graph form, so that you can see that these are different patterns of activation. And the thing is that the same 8 units can represent different concepts just by just changing their pattern of activation across these 8 units. So canary are represented not only by the activation in property nodes, but also by the pattern of activation of other units in the network. This is essentially what artificial intelligence is doing. So artificial intelligence is a simulation of human intelligence and machines that are programmed to think and act like humans. But fundamentally, what makes them intelligent is that they learn from experience. They can actually adapt their programming or their models based on new inputs. And by the way, this is an image that I created in Canva with the prompt, just artificial intelligence. So this is not what artificial intelligence thinks it looks like. This is what artificial intelligence thinks we think it looks like. And the reality, though, is that this is actually more what artificial intelligence looks like. It's servers, it's tons of servers, it's a lot of data right now. But AI really leverages computers and machines to mimic problem solving and decision making capabilities of the human mind, in part by updating its programming based on experience. So AI tries to answer the question, what would a person do next? Similar to this very small scale connectionist model of cognitive knowledge or of semantic knowledge. You can imagine how this might be implemented in an AI model. And in fact, a very small scale AI model that kind of looks exactly like this is your chat or your messaging functions on your phone. If you go into Messenger, like if you have an iPhone and you go into Messenger and you start typing, I like cats more than, see what it comes up with, see what it predicts. It may not actually say, I like cats more than dogs. Your particular phone might have a different prediction based on its experience with you in particular. But you can imagine how these different hidden connection weights can take this input of I like cats and then make a prediction about what's likely to come next. So this is what AI is trying to do. It's trying to predict what would a person do or think or say next. And generative AI chatbots like ChatGPT or Copilot or Claude are powered by these large data sets and computing techniques that really make predictions to string words together in meaningful ways. So they're literally constantly scraping the internet to take all of this information, all of this data, feed it into a large language model, and then be able to produce particular kinds of response patterns, even like text, documents, code generation, images, songs, video. We're getting all sorts of things these days. But this is also essentially how you work. You take in a bunch of input data constantly, all day, every day, throughout your life, and you have integrated it into a large language model called your brain in order to execute certain tasks. So if I had a perfectly predictive AI model and I had a complete record of your entire life and the current circumstances, and I could reproduce that, I would be able to perfectly predict your thoughts and behaviors using a model. But like, I don't have all that. I don't have your experience, and I don't have a perfectly predictive model. But like, you can imagine how the concepts of categorization and semantic knowledge representation in humans looks exactly like this. This is why it's artificial intelligence. So how are connection weights set? We're going to go back to people. This is actually still AI, but this was early AI exercises by cognitive psychologists who were trying to understand how humans might change the connection weights. So in this hypothetical model and a very small scale model. And like literally, I actually think somebody did do this. There was probably a researcher out here who created exactly this program. But in order to illustrate something about how cognition works, not to try to create artificial intelligence. So what you would do, you'd write a program and you would say, okay, I want to create 5 different categories: salmon, canary, daisy, rose, pine. I also want to create 8 nodes that are abstract and undifferentiated at the beginning of the learning. And at 0 learning trials, you can see there's all relatively low patterns of activation, or relatively low activation across all those units, and frankly, no pattern of activation. There's no patterns that are emerging here, which makes a lot of sense. The model doesn't know anything yet. This is a baby, essentially, a model of a baby's cognition. And as you can imagine, a baby interacting with the world or a small scale AI model interacting with the world, it's getting new data. And so in this experiment, the researchers presented a variety of examples to the model and asked it to categorize based on these 5 categories that were provided. Now, you can imagine on a very first trial, you might feed in an image of a rose and ask the system, what is this? And the system on the very first trial is going to be like, salmon. It is literally going to randomly guess. But that guess is going to generate feedback. And that feedback, if you feed in a picture of a rose and it guesses salmon, the answer is like, nope, not right. So it uses that information to then update the model. After 250 trials of showing it various images of pines, roses, daisies, canaries, and salmon, and allowing the system to guess to see what it's looking at, and then giving it feedback, you start to see change in the patterns of activation. And these errors that are being generated in the first sets of trials get propagated back through the system and are used to adjust the connection weights. So after 250 trials, we're seeing some differentiation. 750 trials, we're now actually seeing some very specific patterns starting to emerge. By 2,500 trials, we now have very specific patterns of activation so that new examples are going to be easily categorized. Moreover, one of the things I think is really interesting about this model is that you can see that we know already that of these categories, a daisy and a rose are going to be the most similar. If you look at the pattern of activation, those are the 2 categories that have the most similar patterns of activation too. So you can literally see their similarity through these patterns of activation. So backpropagation is the process by which these error signals that get generated are sent back to network units to provide information about how connection weights should change. Okay, so here's the point in the lecture where you could stop and go finish the H5P activity, models of semantic knowledge, and you can also do the quiz matching paradigms. I've kind of pulled out all of the major paradigms that were used in this module and created a quiz like this matching quiz for you. So finish that up here too. What do babies know? Too much, you guys. Too much. It's not right. Categorization research has a strong link to developmental cognition because forming categories in adulthood is preceded by forming categories in infancy. So if we can figure out how babies do it, it could help us figure out or say something about how adults do it and vice versa. But to do this, you have to be able to reliably determine what babies know. And you can't just be like, hey, baby, what do you think about this? So researchers needed to come up with a reliable way to understand what babies know. And this is where habituation comes in. So the preferential looking paradigm is predicated on habituation. Habituation is learning to ignore things that are not relevant to you or that have no meaning to you. And it's literally like getting used to something or learning to ignore something that doesn't have a signal. And in a preferential looking paradigm, what you typically do is present infants with a series of examples from a particular category until they start to get bored of them. So for example, if you're familiarizing them to cats, you might show like, dozens of examples of different cats in different poses. And over time, the infant is going to be like, first, they're going to be very interested because infants love novelty. But then after a while, they're going to be like, I get it, cats. Yeah, okay, I get it, cats. Once you finish the familiarization stage, then what you do is you present an image of a new cat that they've never seen before that was not included in the familiarization stage, and something else like a dog. And you would use these test stimuli to determine whether or not infants can tell the difference between cats and dogs, or whether they see them as part of the same category. By the way, this I can say from experience, preferential looking paradigm works because babies will stare at novelty. When I lived in Taiwan, babies loved staring at me. They were so rude. They were like legit like, it was bonkers, but also super adorable. But they were literally like, their minds were blown by seeing a white person. It was amazing. Okay, so let's see the preferential looking paradigm in action. This baby is seeing this toy for the first time, and she's like, dope, that is cool. She's getting a little bored, but like, yeah, cool, I like it. But overexposure and time, the infant starts to get bored. They like novelty. She's like, now can we go? Take it up a little bit, and she's still like, nah, boo, I need something new. Woo! Look at that. New thing. Babies love novelty. So using habituation makes a lot of sense in order to understand whether or not they can tell the difference between two things. Okay, so if an infant looks at the cat and is sort of like, oh yeah, that's a new cat, but they see it as part of the previous category, they won't look at it very long. But if they recognize that the dog is a unique or a new stimulus that is not part of the previous category, they will look at it longer. They'll treat it as something new. If infants do not understand that cats and dogs are different, then when you show it the dog, they'll also be like, yeah, cool, I've seen that before. So you can use this to actually really easily tell whether or not cats and dogs are different for babies. I also refer to this as dance monkey dance because infants love novelty, and literally sometimes will get you to dance like a monkey, or like they'll cry. This is something my nephew did when he was a baby. He was either smiling and laughing or crying like, dance monkey, this is not interesting to me anymore. I need something new. Okay, so I'm going to tell you about an experiment where researchers created categories. They made up categories of objects in order to test how infants learn categories. And they would present a series of objects at center, of these made up objects at center to the infants in the familiarization phase. And the experimenters were actually really smart. They created not just one category, but multiple categories and different patterns for those categories. So pattern A had a particular configuration where it always had the two blue objects that were always presented together. It was the third object or the third component that always changed. And I've colored these here for you to see the elements that stay the same across the category, but these were not colored for the infants. That's just for you guys, my friends. But you can see pattern A just had that one feature that was on the top right that changed. For pattern B1, it was the bottom feature that changed, and for pattern C1, it was the top left pattern that changed. So during familiarization, they would choose one of these patterns to present to infants and present that pattern over and over and over again until the infant showed boredom to that pattern. Then they would be tested with a stimulus that was either consistent in its splitting or inconsistent. So the test stimuli were always novel because they had a split in them, and the infants had never seen these objects with a split in them. However, consistent splitting always meant that the two objects that were consistently paired together for that pattern were going to stay together, and the split was the other thing. In the inconsistent splitting category, the split is actually now splitting things that were never consistently paired together. So I want you to think carefully about how to fill in the blanks here. Infants look longer at this test stimuli than the familiarization stimuli. Makes sense because the test stimuli are already going to be novel. And they preferred splitting over splitting. Take a second. So infants look longer at the test stimuli than the familiarization stimuli, and they preferred the inconsistent splitting over the consistent splitting. The inconsistent splitting was more novel than the consistent splitting, and so they looked longer at that. These results suggest that infants picked up on the two co-occurring shapes that defined each pattern type, that they're sensitive to statistical regularities. And the longer looking, they were surprised with the two shapes that had previously been paired together were split apart during testing. It was less surprising when there was a split, but the two shapes had previously been paired together and stayed together in the split. So statistical regularities. But what happens if there are two competing sequences? So the researchers rightly ask themselves, well, okay, we are presenting these categories at center, one at a time, but the world is not nearly that simple. We don't see objects in isolation. Our worlds are complex. They wanted to try to increase the complexity in this experiment by actually producing or presenting two competing sequences. And they would present sequences that pattern C1 might be on the left, pattern C2 might be on the right. And the question that they were asking is like, which pattern are they going to learn? They would use test stimuli that actually, it kind of depended which pattern that they were learning, whether or not this was consistent or inconsistent splitting. So if they looked at this longer, it would tell them which of the two patterns the infant had been paying attention to. But what's interesting is whether this test stimulus is an example of consistent splitting or inconsistent splitting depends which sequence the participant was or the infant was paying attention to. And when researchers added that visual complexity to the display, what their research found was that infants showed no preference between the consistent or inconsistent splitting conditions, suggesting that when you increase the complexity, the infants are not capable of picking up on those statistical regularities. So, how do we learn it then? Like, yeah, the world is complex, and yet infants are still picking up on statistical regularities pretty effectively. How are they doing that? So in a third experiment, Wu et al. Again had these two competing sequences, but now they presented participants, the infants, with a social cue. They had a schematic face that was looking at one of the two sequences and not the other. And what researchers found was that when they gave participants two competing sequences, they could get a novelty preference effect when a social cue was used to tell the infant which one of the two patterns to pay attention to. So what this suggests is that infants use statistical regularities. They do. They are little statistical calculating machines trying to recognize patterns in the world. But then they're also using social cues to determine what stimuli are important. They're bombarded constantly. They're looking to you to see what you're looking at. And that's where they're going to focus their attention. They're using that as a cue to tell us what's important to pay attention to. Okay, so here is where you can go do the assigned reading quiz. It's on Woo et al., but I'm actually going to focus on some components of that article that are not highlighted in my presentation. Okay, so it's the end of this lecture. You should be able to define and recognize novel examples of categories, concepts, categories, and categorization. Describe the advantages of categorization. Compare and distinguish between the three approaches of object categorization. Describe the problems with the definitional approach and recognize new examples of these problems. Describe family resemblance. Describe the characteristics of the prototype approach and its associated findings. Describe novel examples of the associated findings using similar paradigms. Describe the feature of Collin and Quillian's semantic network model and its characteristics and predictions. Recognize novel examples of general criticisms related to the semantic network model. Describe the features of the connectionist models and explain parallel distributed processing. Describe a novel example of the preferential looking paradigm to test infant categorization, and summarize how Wu et al. Demonstrated that infants use both statistical regularities and social cues to learn about categories. See you next week.